Greetings and welcome to the online lecture 3 on unit number 1, that is Advanced Vapor Compression Cycle, on types of transcritical cycles part 2. In previous two lectures, we have discussed basic transcritical cycle and the different types of transcritical cycles. We have discussed three types of transcritical cycle in previous lecture, that is internal heat exchanger type, expander type, and multi-stage transcritical cycle. This lecture we are going to discuss the remaining three types of transcritical cycle. First we'll discuss this is the fourth type of transcritical cycle, that is ejector expansion cycle. In this particular cycle, the main device is the ejector. So ejector is the device. This is the schematic of ejector. It mainly consists of two nozzles. Primary nozzle, this is a primary nozzle, and this is a secondary nozzle. Conversion part, then this portion is called as a mixing chamber, and this is a divergent part. This is called as a diffuser section. So there are two inlets, the motive fluid that flows through the primary nozzle, and the secondary fluid flows through the secondary nozzle. And the mixing takes place in the conversion section as well as in the mixing chamber. And the mixture expands in the divergent portion where the pressure rise happens. So this is the ejector. This is how the ejector works. So the main function of this ejector is to expand the refrigerant, that is the gas refrigerant, from gas cooler isentropically. Expand it to isentropically. In addition to this function, the other two functions, it also assists the compressor. So the function of compressor is to suck the refrigerant from evaporator and also to increase its pressure. So the suction of refrigerant from the evaporator is done with the help of this ejector, and also slightly pressure rise happens in diffuser section. So it assists the compressor in these two features or these two functions, and that's why the compressor work is slightly reduced. Now we'll discuss the cycle right from the beginning. So we start from point number 1. This is a conventional way of explaining any vapor compression cycle, that is the starting point is the inlet of the compressor. So similarly, we start from point number 1. So point number 1 is on the saturation curve. And the reason why, because the one point is connected to the separator, and the separator, it consists of the mixture of vapor and liquid. And if the separator consists of mixture of vapor and liquid, the vapor is essentially a saturated vapor, and liquid is also essentially a saturated liquid. So one point is the compression inlet point. So 1 to 2 is compression in the compressor. 2 to 3 is our desuperating or a gas cooling process in the gas cooler, because it happens above critical point. So everywhere there is a gas, so there is no condensation takes place. Then at point 3, from the refrigerant is very high pressure, high temperature refrigerant. So this high temperature, high pressure refrigerant is made to flow through the primary nozzle. So this is a primary nozzle where it expands isentropically up to 0.4. So up to 0.4, that is this is the pressure, that is the ejector pressure. So this is the lowest pressure in the cycle. So up to 0.4 it expands. Now from 0.10, again the mixture of the primary fluid and secondary fluid, that mixture is further flows to the divergent portion where its pressure increases isentropically again. So 10 to 5, the pressure rise in the diffuser section. Then 5, then it enters into the separator, and because 5 point is in the wet region, so means it is the mixture. So when it enters into the separator, the vapor and liquid separates. So that is denoted by point number 1 and point number 6. And both states are saturated, that is saturated vapor and saturated liquid. So at point 6, that at the bottom there is a liquid, at top there is saturated vapor. So 0.6 is on the saturation curve, on saturation liquid line. So 6 to 7, that is expansion in expansion wall. So as this is this happens in expansion wall, that's why it is isoenthalpic expansion process. 7 to 8, that is evaporation process that happens in evaporator. That is 7 to 8, considering the state of refrigerant, the outlet of the evaporator is saturated. So 8, then at point 8, it enters into the secondary nozzle, and when it flows through the secondary nozzle, it expands again isentropically in this case. So 8 to 9, that is expansion of refrigerant till the ejector pressure. So that till the ejector pressure. So point number 9, that is the state of refrigerant in the ejector at the state of refrigerant of state of secondary refrigerant in the ejector. And point 4, that is state of motive fluid or primary refrigerant in the ejector. So point 4, so there is a mixing takes place of primary fluid and secondary fluid, and the mixing point is point number 10. So this completes the cycle. So this ejector expansion cycle, because here the main role of ejector is to expand the refrigerant that is coming out from the gas cooler. But in addition to that, the ejector also helps to suck the refrigerant from the evaporator, as well as compress it to slightly to compress the pressure. So due to this, it reduces the compressor work. So this much pressure rise that happens in ejector. So the considerable COP development is taking place, because already due to isentropic expansion, already that point 4 is shifting, because if it is isenthalpic expansion, point 4 is somewhere here. So point 4 is already shifted towards left. And also this compressor work is also reduced. So there is a double effect. So it increases the refeeding effect by shifting the point towards left, and also it reduces the compression work. That is by increasing pressure slightly above the evaporator pressure. So one researcher, he showed that is Teng and et al. In 2007, he showed that the ejector improves the maximum COP up to 18.6% compared with the internal heat exchanger, and with greatly reducing the throttle losses as well. So this is how the ejector expansion cycle works. This is a pictorial view of ejectors, which is sometime it is made up of material, but preferably it is made up of copper material, but sometimes it is made up of also the plastic material as well. It's a small component, and it also saves the space as well. So this is coming out as a potential modification of transcritical cycle. This is the fourth modification. Then the fifth modification or fifth type is vortex tube expansion cycle. So in this particular cycle, vortex tube is the main device of this cycle. So this is vortex tube. So again, like ejector, there are also three inlet outlets. So there are one inlet and the two outlets. So let me explain the function of vortex tube. Vortex tube, it consists of a small tube, and where any air or any gas, it enters tangentially. When it enters tangentially, it creates vortices. So when the compressed gas or compressed air, when it enters into the uh, vortex, because there is a tangential entry to the tube, and due to this tangential entry, the vortices are created. So this is outer core, which flows towards right, and there is a control valve provided at the right side. And due to this control valve, there is a return. This particular outer core is returns, and that is called as an inner core. So there are two cores developed in the vortex tube: outer core and inner core. So outer core, where it absorbs the heat from the inner core. So inner core becomes cool, and outer cores become hot. And depending upon the openings, the hot gas or hot air, it accepts from this particular exit. So this is hot exit, and the cold core, which flows through the inner side, and it becomes cold because of dissipation of heat to the outer core. So this core again made to flow through the orifice, so its further temperature decreases, and this cold air or cold gas, it made to flow through this particular exits. So there is one inlet and two outlets, one hot outlet and one cold outlet. So similarly, this is hot outlet and this is cold outlet. So when it is made to flow through this particular condenser part or evaporator, so it becomes a cold. So this is a hot gas. So it enters into the vortex tube tangentially, and due to this, it creates two outlets, one hot outlet and one cold outlet. So hot outlet is again further cooled in desuperator, and the cold outlet that is again enter into the evaporator. But due to this expansion, some liquid is generated. So liquid is there. So that liquid is collected in the pan and that enters into the evaporator. So this mixing takes place of the cold gas and the saturated liquid, and that mixture is entered into the evaporator to absorb the heat. So this is what the vortex tube. So this is a pictorial view of the vortex tube. It looks like it is made up of copper or stainless steel, mild steel. Uh, so let me explain the cycle again. So again, we start from point number 1, that is a compressor inlet. So compressor inlet, unlike the previous case, the compressor inlet is not on the saturation curve because it is a mixture of saturated vapor coming out from the evaporator and superated vapor coming out from the vortex tube. So the mixture state is not saturated, it is slightly superated. So one point doesn't lie on saturation curve, it is slightly in the superated zone. So this is point number 1. So 1 to 2 is the compression in the compressor. So 1 to 2 is the compression in the compressor. Then 2 to 3 is that is desuperating part. So correct this. This is not a condenser. This is a desuperator or gas cooler. So in the main diagram, already the notes provided. You correct this. This is a desuperator. Then 2 to 3, that is a desuperating part. Then at point 3, then it enters into the vortex tube, the inlet of the vortex tube. When it made to flow through this vortex tube, it expands. But there are two outlets, one hot outlet and one cold outlet. So hot outlet is a superated vapor. So the superated vapor, it is denoted by this H point. And C point, it is the saturated vapor. So it is denoted by this. So these are the two outlet processes. And we cannot explain this is with the help of thermodynamic processes. So it is a totally irreversible process or imagine. So we cannot describe this process whether it is isentropic process or isoenthalpic. So only by locating the points, we join point 3 to H and point 3 to C. That is a cold end and hot end. There is one more outlet that is only a saturated vapor. So in the vortex tube, so the gas exit from two outlets, but the remaining liquid, it is maximum liquid is there. So that liquid is collected in the pan and that enters into the evaporator. So that as this liquid is just converted, so that it is obviously a saturated liquid. So it is denoted by point number 4. So point number 4 and point number C mixes. So this is point number 4 and this is C. So mixing of point C and 4, that mixture point is point number 6. So this is point number 6. So 6 to 7 is again evaporation in the evaporator. So 6 to 7 is the evaporation, and 7 and 5 mixes. So 7, that is a refrigerant stream coming out from the evaporator, and 5, that is this is desuperating, that is from H to 5, that is desuperating takes place. So that resulting point is point number 5. So point 5, that is coming out from the desuperating, and 0.7 that is coming out from the evaporator. They mix and the mixture point is point number 1. So this completes the cycle. So vortex tube expansion device, again, it is slightly complicated, but if you rewatch this video, you could able to understand the exact working of this particular cycle. The maximum increase in COP using vortex tube or the expansion work output device, assuming ideal expansion process, it was around 37% compared to the one that is in isenthalpic expansion. So this is effective expansion process, but this is the ideal case. But due to less efficient, because vortex tube is the device which has a very low efficiency. So generally the efficiency is 0.2, 0.3. And because of this, the COP improvement is around 10% only. The size of the vortex tube is very small, so it doesn't occupy the more space. So still it is recommended modifications. So this is the 4th time, that is vortex tube expansion cycle, where the vortex tube is used as a main device for expansion. In the previous that is ejector is used as an expansion device. Here the Otex tube is used as an expansion device. Then the sixth and final type, that is a parallel compression economization. So in this case, the compression happens simultaneously. That's why it is called as a parallel compression. The compressor of gas coming out from the evaporator and the compressor of the gas coming out from the flash chamber, it compresses in a single compressor simultaneously. That's why it is called as a parallel compression type transcritical cycle. So again, we start from point number one. So point number one is again at the inlet of the compressor. So inlet of the compressor. So 1 to 2 is compression of the gas coming out from the evaporator up to the gas cooler pressure. That is point number 2. Then 7 to 8, that is a compression of the gas that is coming out from the flash chamber. So 7 to 8, that compression of the gas coming out from the flash chamber. And the 2 and 8, that mixes, and the resulting mixing point is point number 9. So we cannot locate point number 2 and point number 8 on schematic diagram, because at the outlet the mixture is coming out from the compressor. So point number 9 is the mixing point. So 9 to 3, again the expansion in the gas cooling in the gas cooler. So point number 3, so that is constant pressure gas cooling. So at point 3, then it enters into the expansion valve. So the refrigerant is expanded at up to the intermediate pressure, that is a pressure of flash chamber. So at point 4, again it enters into the flash chamber where it separates. So the separation point. So again, this is a mixture of saturated liquid and saturated vapor and saturated liquid. So both states, that saturated liquid state, it is denoted, it is shown at the saturation curve, that is on saturation curve, and 0.57, that is a saturated vapor, it shows on the saturation vapor line. So 0.5, it is further expanded in the second expansion device, that is 5 to 6, and 6 to 1 is the evaporator. So 6 to 1 is the evaporation taking place. So this is a parallel compression type transcritical cycle. It is called as because the compression from the gas coming out from the evaporator and compression of the gas coming out from the flash chamber happens simultaneously, it compresses simultaneously. This reduces the compressor work slightly, essentially, but in order to use this particular compressor, it's essentially a axial flow compressor, because Bredoff concept is used here. So this is one inlet and this is secondary outlet, secondary inlet. So at the intermediate state, so it enters. That's why so slightly the pressure increases, and at the intermediate state, the second stream enters. So this type of construction is used in the compressor, and that if we have to use this particular configuration or modification, then essentially axial flow compressor need to be used, because such facility we cannot develop in reciprocating compressor as well as centrifugal compressor. So this type of combination or this type of modification increases the cooling capacities up to 15%. So this is a sixth and final type of modifications. So there's 6 type of modifications we have discussed. And if we compare these 6 type of modification on the COP improvement background, so it is found that the turbine type or the expander type transcritical cycle produces the maximum improvement, is around 35 to 40%. And that is because of the positive work developed by the expander. So because of that added positive work, so both work input, work input is reduced from the prime mover as well as the refeeding effect input. So because of the double effect, there is a highest improvement seen in the turbine type, and the lowest improvement seen in the internal heat exchanger type, and others are in between. So with this, we have finished all 6 types of 6 modifications of the transcritical cycles, and all the modifications are generally made to shift the point 4 towards left, that we have discussed in the first lecture. So these are the 6 modifications. So at the end of this particular topic, you should be able to explain the working of ejector and ejector expansion cycle. Secondly, you should be able to explain the working of vortex tube, how vortex tube works, and the vortex tube CO2 cycle. Then how the parallel compression system works, and what are the limitations of parallel compression system, which type of compressor is generally suitable for this type of compressions. And you could able to quote also the most efficient CO2 refrigeration system, that is the most efficient modification. That is obviously the expander type. But there are some physical constraints of expander type. So, theoretically, it proves that that type of modification produces the maximum improvement. So with this, we have finished the first segment of the unit number 1. So that is advanced vapor compression systems. So we have finished the transcritical systems, basic transcritical cycle, and there's 6 modifications. And all these modifications we have discussed. Exam point of view, these modifications are generally asked, that is the construction working of these modifications, the important features. With this, we have finished the first segment. From next lecture onwards, we'll discuss the second advanced vapor compression cycle, that is ejector-based refrigeration cycle. So it is a compressor-free refrigeration system, and there are again 4 to 5 modifications used there. So that these modifications also we'll discuss. Thank you.